Physics Part 113. In some ways, the fact that the gas is made up of such an enormous number of molecules is an advantage. It means that we can give a large-scale description of the gas in terms of only a few variables. These variables are quantities such as pressure P, volume V, and temperature T. These variables are about average conditions in the gas. Instead of describing the behavior of each molecule, we have already met the experimental laws relating to these quantities. Our aim is now to relate the ideal gas equation, which deals with the large-scale macroscopic quantities of P, V, and T, to the small-scale microscopic behavior of the particles of the gas. We shall do this by taking averages over the very large numbers of molecules involved. We shall find that we can derive equation from Boyle's law when we make very simple assumptions about the atoms or molecules which make up the gas. This is the kinetic theory of an ideal gas. We shall also see that temperatures can be related to the kinetic energy of the molecules of the gas. Before we go too far with this model of a gas, is there any experimental evidence for believing that its molecules are moving around all the time? In 1827, biologist Robert Brown was observing under a microscope tiny pollen grains suspended in water. He saw that grains were always in a jerky, half-circled motion. Even though the water was completely still, this movement is now called Brownian motion. If we make the assumptions that the water molecules are in rapid random motion, then it is easy to see how the pollen grains could move so jerkily under the random bombardment from all sides of the water molecules. We can also produce Brownian motion by observing the motion of a tiny soot particle in smoke. These particles too move in the jerky manner of Brown's pollen grains. Thus it seems that the molecules of both gases and liquids are in the rapid random motion as required by the molecule model. Nearly a century later, Einstein made a theoretical analysis of Brownian motion, and from the masses and distances moved by the suspended particles, was able to estimate that the diameter of a typical atom is of order 10 power raised to minus 10 m. If we are able to think of gases and the liquids are consisting of large numbers of atoms or molecules in rapid random motion, what about solids? The obvious difference between a solid and a liquid or a gas is that the solid has rigidity. However, the microscopic model explains this, suggesting that the atoms are held in more or less fixed position by much stronger inter-atomic forces than exist in liquids or gases. This is because the atoms are arranged quite close together in a solid, whereas in gas there is a great deal of empty space. Atoms in a solid can still move, but their motion is restricted to vibration about their equilibrium position.